Welcome back to Machine Learning for Engineers. Today we're going to talk about how this case study relates to visualization exploration with concrete data. So come to the course website and then scroll down on the right to the concrete strength. And once you're there, we're going to give a description of what we're going to cover today and then do some example code and walk through this exercise together. So concrete mixtures have several variations. This data set is a case study for data visualization exploration to predict the output label, which is our concrete compressive strength. So we want to know what is the strength of our concrete. And there are several input factors that have correlation to this output, the concrete compressive strength. We're going to use visualization and exploration to gain understanding of the data and make some decisions about how it can be applied to predict strength. So these are some of the input features that we're going to look at. We have cement, blast furnace, fly ash, water, superplasticizer, coarse aggregate, and fine aggregate, and finally the age of the concrete. So all of those are going to be used to predict this final concrete compressive strength. We have 1,030 concrete samples, and those were obtained from this data set that's on Kaggle. Okay, so let's just look at those. Okay, here's the data. There are separated values, and you can scroll down and see all of the values. All right, we're going to import this, but first of all, if you want to just grab this Jupyter notebook, you can also use it on Google Colab, allow you to run it through a web browser without having to install anything. The second example that we're going to run through, not on this video, but a future one, is Jupyter Notebook on GitHub for this classification regression case study. But for now, let's come here, and you can go to GitHub, just right-click here, or you can clone the archive and save it to some place where it makes sense. Okay, I'm just going to save it to the desktop, and then I can close this now. Okay, so there it is right here. If I refresh, I can open up this concrete strength, and let's go ahead and just go through this exercise together. So most of these are going to be pre-filled in, but there are going to be a few places where you're able to try it out yourself with some challenge problems along the way. So let's go here. We have some packages that we want to import. All right, and then let's go ahead and just read this data in. If we want to read the first 20 rows, we can just change that to 20 instead of 10. So we can see some of the values here. That one doesn't fit all on the screen, so I'm just going to reduce that down to 5. All right, let's go on to one-dimensional plots. Those are useful for plotting distributions of a single feature or label. So just one column at a time, and you're looking at the data, trying to investigate outliers in that data or other things that might be there that are going to cause problems. All right, so let's go ahead and run this one. This is for the cement concentration. And we see a histogram, a density plot, box and whisker, and also a violin plot that combines this quartile plot that you see here, the box and whisker, with the density plot. So it overlays both of these together, so you can see quartiles and the distribution together. So this was one of the more useful ones, but these are kind of standard histogram and density as well. All right, so let's create a series of one-dimensional plots to visualize the distribution of concrete strength, and that's called CSMPA, concrete strength in megapascals. All right, so what we can do is just copy all of this and then just change our data label that we want to see. So this is going to be CSMPA. And now we have our output label instead of the cement concentration. We can see there may be some outliers up here. You can see the upper and lower limits. Sometimes they put these extra circles outside of that if it determines that they might be outliers. All right, here's our histogram There's our density. So we have some that are very high strength concretes, but most of them are in this region right here. And we can also see that with the violin plot as well. Okay, our median value is right around 35. Okay, let's go on to two-dimensional plots now. So these are particularly useful to show correlations between two features or between a feature and an output label. So this is very useful in the early phases just to see general trends on how some of these input features relate both to other input features for, if they're going to be collinear or too highly correlated. It means that those two features could potentially be just down selected to one. And if there's a good strong correlation between an input feature and the output label, you may favor using that one over others. Alright, so there's things like line plots, scatter plots, pair plots and joint plots, heat maps, and grouped 1D plots. So here's the first one. Here's the cement concentration. So that's how much we added relative to the other ingredients versus the compressive strength. So you can see that, as generally as you add more cement, you generally get additional compressive strength. But you still have some values, even with high cement, it still has low compressive strength. All right, so here's a pair plot. So if you run it, you can see this one on the diagonal has the cement, okay, versus cement. Okay, so that means that when it's a variable versus itself, it's just going to be the histogram of the distribution. And then we have in the off-diagonal areas, this is where we see, for example, CSMPA versus cement and versus slag. All right, and as you add more slag, maybe that decreases the compressive strength because the relative concentration of something else might have gone down. All right, and then you can see this distribution of CSMPA. The joint plot is nice because it combines a couple of those together. So this is CSMPA versus cement, and we see the scatter plot, and we also see the distribution on this top horizontal and then right vertical axis. Okay, a heat map shows a correlation between features. One means that they're exactly correlated, and -1 means that they're inversely correlated. So the white ones right along the diagonal, cement is obviously correlated with itself perfectly, so that's going to have a value of 1. And then as we go down, we can see the 0 values are about right here, and then we also have negative 0.6. So they're highly negatively correlated. Okay, water and superplasticizer, for example. The ones that we're really interested in, though, are the CSMPA versus all these other variables right here. All right, let's go on to a grouped 1D plot. This is a group we've grouped, with this 35. That was our median value. And we're just going to say that high strength is greater than 35 and less than 35 is low. So what I've done here, let me break this into maybe 2 cells just so I can see it a little bit better. I'm going to insert a cell below and then just print the data frame head. All right, and let's go with 20 values. And so we can see some that are low here. Okay, so that was below 35, so we gave it a low label. And what that does is it allows us to see, between low strength and high strength. It allows us to segregate those two so that we can see some of the factors that might have contributed to the strength of the concrete. So we use the where, the NumPy where. Okay, and this is going, if it's true, if it's greater than 35, then I'll make that high, and if it's false, I'll make that low. So it's just going to make this column of data that we put right here into our data frame. And we called that strength. All right, so let's go down to the violin plot now. So now we have, our x is going to be the strength, and the y is the cement. So we're going to look at the distribution of cement between the high strength and the low strength. So you can see the low strength, in general, those have less cement in the concrete samples. All right, so let's come on down to this activity where we're going to generate two types of two-dimensional plots using two features of your choice. CSMPA would be a useful feature to include since it's the output label or feature you want to predict with regression later. So let's go ahead and let's see, select a couple here. I guess we could choose, let's just go look at our columns first, just to remind ourselves of what they are, okay? And if you want to, you could do something like for x in data frame columns, and then we'll print x. And then it shows us some of these, and then we can insert a cell below. So we want to create two types of two-dimensional plots using two features of our choice. So let's just stick with this violin plot. And instead of, let's see, I'm just going to do, let's take another look at, let's see, violin. This is not really a two-dimensional plot. It's like a one-dimensional plot, but I have this extra dimension of strength right here. So let's just look at age. Okay, so we can see some of the higher strength. Those are the older ones. But the distribution is, in general, most of these are 150 days and below. Or I could take a look at, let's say, slag. Okay, or some of the other ones. So this is just an example of a violin plot. Let's come back up here and, oh, I missed the, okay, I got the heat map. Okay, we already did that one. Let's look at our joint plot. This one has a lot of information in it. Okay, so let's see, come down here, insert another cell. And instead of cement, let's look at fly ash, for example, and generate our joint plot. Okay, so we can see a lot of the samples have 0, which kind of comes out in this distribution right here. All right, and so this one's somewhat of an imbalanced data set because we have many of them that have no fly ash, but then the other half that do. And you can see the range of CSMPA, and there's maybe just a slight decrease as you increase fly ash, the strength goes down. All right, and then we can look at multi-dimensional plots as well. And these visualize more complex relationships. However, this natural intuition starts to break down as you have more dimensions. So you can animate the plots. That's one way. It's kind of like this time element, and create some type of movie that changes the distribution as you go. That'd be another way to fit another dimension in there. Or you could do something like a three-dimensional scatter plot. So I'm just going to run this one to show how we do a scatter plot with X, Y, and Z. And I've just created those from cement, slag, and fly ash. All right, and I need to have this add subplot and do the projection equals 3D. Okay, so we can also group by type, and so you can vary these points by size or by hue. And this one's really nice because you can it really comes out, the high strength ones are the darker ones. Okay, but let's say maybe we wanted to do it by size and hue. All right, so let's go and just add one more here. So I'm going to create a new subplot, and I'll make that my third one. So this is the number of rows, number of columns, and then that's the order, the one that you're currently working on. Alright, so let's just change by hue and size. So I'm going to copy this one and scatter plot and do size equals, and then let's have that way Z as well. Okay, by hue and size. So when I do this one, then I've increased the size, but then also made them darker. Okay, so let's go on to principal component analysis. This one seeks to do some data reduction. So if you have higher dimensional, you know that your inputs are highly correlated. Sometimes you can reduce that down into a subset of features that are linear combinations of the others. So let's just show it by example here. Okay, so we have principal component analysis. I'm going to include the scatter plot here. But let's just include in this activity below, we'll perform a PCA using only two features. We'll plot the results of the PCA and scatter plot of the raw data, and if they're different, if so, how and why. So we first of all want to create a multi-dimensional plot of at least 3 features and plot them. Alright, so let's just do a 3D scatter plot, but just change some of the features that we use. Alright, I'll grab this one. Alright, so let's say we want CSMPA as our z-axis instead, and I'll just put that as CSMPA. Alright, so it shows the strength of those. Let's do this principal component analysis now. What I'm going to do is just grab this code right here, and let's just include, instead of data frame columns all the way to the second to last one, we just want to include 2 of them. So let's just include 0 to 2 and then plot. Okay, so I've just included 2 components instead, and now we can just plot the original ones as well. So here's a scatter plot of the transformed one. So that's for dimensionality reduction, but I only have 2 to start with anyway. So let's just include a label here. I'm going to change this to an X, and this is the PCA result. Alright, and I'll do plot legend. Okay, because I'm going to be adding these additional points on here. Alright, and then let's just do another scatter plot. And instead, this one's going to be data frame. And I'll just do data frame column 0. Alright, there's my first one. So I don't even need to know the names of those. I'm just taking the first 2. And this is going to be original. Okay, so the PCA, it rotates it into principal directions and then gives eigen values that tell you the magnitude of those directions, and so it's this basically just rotating and transforming these original data so that you separate it out into these principal directions. But if you only have 2, there's really no advantage to doing that. Okay, you're not reducing your data down. Maybe you could see if they're highly correlated, you could just have a single dimension, so it'd be a linear combination of the 2 original ones. Okay, I could change this as well. I could say, let's select 2 to 4. Okay, so 2 and then 3 here. Okay, so you can see how this one is transformed down here into this principal direction here, which is, it could be a linear combination of these 2. Let's just see what those are. Data frame columns 2. Okay, that's fly ash, and the third one is water. So perhaps when the two are related somehow, or maybe one of the dimensions is not as important as the other. Okay, so there's PCA that with 2, we've just plotted. Are they different? Yes, they're different. It transforms it and rotates it. Okay, so other plotting options. There's also Plotly, which is really nice. Plotly creates these 3D scatter plots that you can rotate them around, mouse over it. You can zoom, and do other types of rotation. So Plotly is a nice way to have this interactive, be able to see the data from many different angles, and maybe you want to change that to CSMPA. Okay, and look at some of the features here in 3-dimension. All right, the other thing is Pandas Profiling. And we reviewed this in the prior video just about visualization, but this was a very nice package for generating a lot of this summary data that's pretty standard when you're working with data for the first time. There's also a minimal flag here. Right now by default it's false, but if you set it to true, it skips some of the steps that would otherwise take a long time. So there's only 1,030 data points, but if you get up to like 10,000 or something like that, sometimes these correlation plots can take a little while to generate. So let's look at our data. We have a 1,030. We have some duplicate rows. Okay, so 2.4%. That might not be a problem. Maybe the samples came out the same. So then we go to warnings. We have a lot of zeros for slag, and fly ash has a lot of zeros as well. Super plasticizer also has a lot of zeros. Okay, and then we go to variables, and this one's nice because we can see the distribution, and almost like you were describing the data for each one. So we can go through and look for any problems, outliers, or other things that might be an issue with our data. Okay, and there's strength. So we want these to be somewhat balanced if we're going to be doing classification later as well. All right, we can look at interactions. This one, maybe by CSMPA, I want to go through and look at fly ash versus CSMPA, or water versus CSMPA, super plasticizer, coarse aggregate, and fine aggregate, and age. All right, and so you can select these. It's a nice way to just browse through some of your parity plots. All right, here are the correlations. This one, I like how it does this one a little bit better, because any of them that are white, this one kind of shows there's not a strong relationship there. All right, and if they're blue, then it's positive, and if it's red, then it's a negative correlation. All right, there's spearmints, Kendalls, and 5K. And then you can look at missing values as well. There's this sample, the top 10 rows, the bottom 10 rows, and then look at this report over some of the duplicate rows that are present. So it looks like these 5 right here are duplicate, and these 5 are duplicates. Actually, they're not duplicates. The age is different on those, but there's some values that are duplicated here. Okay, so anyway, that ends this tutorial on data visualization and exploration. The next one that we're going to get into is going to be this concrete strength, and we're going to do part 2 of it. So come back here for this one as well, for regression and classification.